Before we get started, I wanted to mention that, remind you that next Sunday, we will have another program when Sonia Waddell, who is an economist with the Federal Reserve in Richmond, will be speaking. Her topic is Focus on Growth, Virginia and the Northern Neck, specifically 2020. So I hope many of you will come and spread the word among your friends. And now I would like to have Lovey introduce our speaker.
Thank you, Gloria. We welcome Stewart Lamerdin. He is our speaker. He is the Director of Marine Operations at VIMS. He holds many advanced degrees, and if I tried to list them, you would hear me and not him. He is responsible for all the aspects of at VIMS fleet of over 30 vessels. And when I told a friend who is very familiar with VIMS that they had 30 vessels, and he said, I couldn't believe they had that many. He's also responsible for the field support of the program. I'm going to turn the mic over to Stewart. I was a teacher, I can talk all day. We are very glad that you are here. This busy man is here to tell us about the RV Virginia, which he's in charge of. And you may have seen it anchored on Carter's Creek. And he will tell you why it's not at Gloucester Point.
I have one of these guys here, so I can give you this back.
Okay.
Yeah. Well, thank you, everybody, and I just can't say how much I appreciate the opportunity to come chat with you folks about a topic that I truly enjoy. As Lovey mentioned, I've spent a little bit of time in the classroom with some of the degrees that I've had and opportunities, but my true love is going to sea and doing oceanography and studying the marine environment. And I made a slight shift early on, not to go too far, but I made a decision at one point where I had an opportunity to pursue a PhD and go on to write papers and things like that. Or there was an old research vessel captain who said, you know, you really should think about coming to sea with us for a trip or two and then make a decision. And ever since then, I've enjoyed going to sea and studying marine research and helping to facilitate marine research. So with that, I'll get rolling here. I'm assuming everyone can hear me back in the back? Great, great. So I'm sort of an interactive speaker here, so it might be a little different than others, but I want to start out first with some acknowledgments and maybe an apology, but acknowledgement-wise, while I'm speaking about the Virginia now, I'm relatively new to VIMS. The Marine Superintendent before me, the Director of Marine Operations, was a gentleman named Duran Ward, and it was through Duran Ward's efforts and a number of other folks that this ship really came to be. So I definitely wanted to acknowledge Duran, and I don't care how good of a ship you have, unless you have a good crew for it, it's not worth anything. And the Virginia is lucky to have a group of folks that are truly an excellent crew. The captain, John Olney, the chief engineer, Keith Mayer, one of our mates, Reed Kirkpatrick, and one of our aspiring engineers, deckhand and mate, Taylor Moore. So those are the core group of folks that helped to facilitate this. And my apology is really more an acknowledgement that, just like I said, I'm relatively new to VIMS and to this area. I've been at the Virginia Institute of Marine Science, VIMS, here for less than a year, so I'm still getting to know things. So for those out in the audience, if I misspeak on something or heaven forbid I mispronounce one of the rivers you have around here, I will apologize in advance. So what I wanted to do in this talk was just basically go over a little bit about research ships from the past, a little bit about what VIMS has in the present, and then spend most of our time hopefully chatting about the research vessel Virginia, the vessel that you see here. So let me make sure my pointer works, maybe. And it sort of works, sort of doesn't. I knew we'd have some technical difficulties. Go on now. Go on now. Well, I'll tell you what, we will adapt. So, what is a research vessel? Probably not this one. Research vessels, in general, have a purpose, as I like to say to them. And there's clearly been a lot of vessels in the past that have gone out with and explored areas. But a research vessel is a little different. An oceanographic research vessel, as is defined by the Coast Guard, is any vessel that's engaged in research and education focused on limnology and oceanography. That's the formal definition of that. And that's one of the definitions I like to hang on to as I consider what a research vessel is. There's been a lot of vessels that we could consider research vessels in the past. I picked out a couple of them, and I'd say these are fairly close, but I wouldn't call them research vessels per se. We have the Victoria here that Magellan sailed on when he circumnavigated the world, you can see down here. He had Captain Mendoza on board, who didn't make it the entire journey as his crew, and he differed, and he ended up not making it the entire journey, and Captain Barbosa took over afterwards. And neither did Magellan, for that matter, as he passed away on the latter part of the voyage in a dispute in the Philippines, I believe. The Endeavour, Captain Cook. Now, why wouldn't this be a research vessel? It's clearly circumnavigated the world 3 times. I would argue that the motivations, let's say, were a little different than what you'd have on an oceanographic research vessel. I think Captain Cook was focused on the explorations and perhaps maybe the exploits of this exploration as well. And as we know, on his 3rd voyage, it didn't end up very well for him either. In Hawaii, he was had a disagreement with the locals there and didn't make it out of Hawaii. And even our friend Ernest Shackleton, who some of you may have known, had the Endurance there all the way on the right. Again, there were some scientists on board, but I think one could argue that his focus, again, was a little bit more adventurous, a little bit more about exploration. And we also know that he probably wasn't a research ship because the way he went about recruiting for people to participate in this journey was, for those that can't read this, was that an ad he took out that just simply says, "Men wanted for hazardous journey, small wages, bitter cold, long months of complete darkness, constant danger, safe return, doubtful, honor and recognition in case of success." So I don't know too many scientists that would be interested in that. And there is some truth in advertisement, as his vessel was eventually crushed in the ice, and he embarked on one of the more epic journeys that has ever been recorded. If you haven't seen it, especially since we're in the library here, there's a great book by author's name is Lansing called Endurance, and it is one of the best adventure stories about how Ernest Shackleton and some of his crew made it back from Antarctica. But nonetheless, we'll move on to things that I think really are some of the first research vessels that I think really represent what a research vessel is. We see here the research vessel Albatross, and it was launched, as I say here, in 1882. And this was a purpose-built vessel that was built for at that time, United States Fish Commission. And it was really started because, somewhat on an economic bent, that people were wondering where the fish were going. This was primarily on the East Coast. It was a 234-foot ship that cost about $148,000 to build back in 1882, and it was built in Delaware. What made this vessel somewhat unique is that it worked all over the world, all over the different oceans, the Atlantic, the Pacific. And what was also interesting about this vessel was that it was likely one of the first government vessels to have electric lights on it. So Edison actually played a role in outfitting the ship with electric lights on it. The Albatross, you guys may have heard the name of that vessel, or there's probably a number of them, but in the research community, there's a number of vessels. There's the Albatross 1 through 4, if you will. So over the years, people really enjoyed the name and continued on with it. But we can see here back in 1882, a vessel that was exclusively engaged in marine research. Soon after that, another, I'll consider somewhat epic research cruise took place on the Challenger. And so this was a vessel that was launched in 1858 and was initially stationed down in Australia early on to keep the peace, if you will, and then soon was transitioned into, or was chartered to conduct, again, a round-the-world scientific expedition. It resulted, the voyage took place in 1872, and it involved a 69,000-mile journey that took place between 1873 and 1876 and occupied 360 stations around the world's oceans. And what was interesting about this ship was that one of the more unique aspects of it, it had what they called a dredge on board. It was essentially a very large winch that allowed them to take samples throughout the ocean to determine the depths of the ocean, since no one really had any understanding of how deep some of these places were. And it was actually was able to sound the deepest place in the world's oceans, in the Marianas Trench, which is still known today as Challenger Deep. So again, the deepest place in the ocean was named after this vessel. They had a winch on board that was capable, and I think the word was that they had 181 miles of line on board to make these soundings everywhere in the world's oceans. So the outcome of that was also pretty spectacular when you think about it. There were 50 volumes and almost 29,000 pages of scientific research that came out of those voyages. And again, even into more of our modern times, the Space Shuttle Challenger was actually named after this vessel. So it truly a research vessel in the classic sense of the word. I picked another one. This is we won't call it a research vessel per se, but it did conduct some seminal research. This is the merchant vessel Fram. This was launched in 1892 in Norway. And this carried a seminal oceanographic scientist, and I'll mispronounce his name, Fridtjof Nansen, or just simply Nansen as we know him. And he was instrumental in assessing the Arctic current flows, especially and associated with the North Pole area. Because as we know, there's no land once you get up where the North Pole is, so not many people knew what those currents were doing in that area. And Nansen not only did help to document some of the current Arctic current flows up there, one of his vessel captains, Captain Sverdrup, was Nansen actually named a type of movement of water after him. It's a way a current particularly moves, so it's called a Sverdrup as a unit of measure of large ocean currents moving. But also, one of the things that I thought was really interesting about Nansen was he was also instrumental in developing certain ways of collecting water for oceanographic research. And I pointed out here, this drawing right here, which is hard to conceptualize, is called a Nansen bottle, and it's still called a Nansen bottle today. This is a way of collecting water at a specific depth. So as you can imagine, if you wanted to collect something at, let's say, 100 meters of water, and you just wanted 100-meter water, you'd have to lower something down and then trigger something so you could close a bottle and then bring it up, and then you could study that particular water that's specific from that depth. He invented this particular way of sampling this. This is a more modern picture of one that was probably used all the way up until probably the 80s, 1980s or 90s, and then we moved into these Niskin bottles that are a precursor of these. But this was all developed by Nansen, a way of collecting water at specific depths. And he was also instrumental in utilizing something that the folks on the Challenger expedition developed, which was something called a reversing thermometer, which is another interesting way of taking a mercury-filled thermometer, and one of the things that the scientists were very interested in, especially on the Challenger expedition, was what were the temperatures of water at deeper depths. So they had no real way of measuring that. We didn't have long conducting cables to figure out what the water was down there. So they developed a way of lowering a thermometer down into the water, and then at a certain depth they could drop a messenger. You kind of see one here. It's a big chunk of metal, and it released the bottle, or in the case of the reversing thermometer, it released a mechanism by which the temperature at that time, the thermometer completely flipped over and separated the mercury apart. It's kind of hard to conceptualize, but essentially it fixed the mercury at a certain place in the thermometer so that when the scientists recovered this thermometer, the mercury would be fixed, if you will, exactly where to correspond with a certain temperature. All developed on the Challenger expeditions and perfected out on the Nansen expeditions on the Fram. The Fram also has an interesting past where it was the past where it also was the vessel that carried Raoul Amundsen to the South Pole, the first person to reach the South Pole. The Fram was his vessel that he took down because of the successes that Nansen had in those areas. It has one of the more unique hull designs, as opposed to Shackleton's vessel, as you saw, that was crushed in the ice. So when you go in and the ice is open and the ice comes in around you, there's so much pressure when the ice comes together, it'll crush a boat. The Fram's unique characteristic was that not only did it have a copper bottom, but it was rounded enough so that as the ice came in to squeeze it, it popped up on the ice, as opposed to being crushed by the ice. So it allowed it a better opportunity to survive being frozen in the Arctic there. So, and I would say those are some historic research vessels that I think set the precursor for more modern vessels, but I would be remiss, given that we're in a library here, if I didn't mention a couple references to research vessels in modern, or in literature. Here on the left we see the fishing vessel Western Flyer that John Steinbeck and Ed Ricketts took down to the Gulf of California, where Steinbeck ultimately wrote The Log from the Sea of Cortez, which is a fascinating tale of less about science and more about the uniqueness of working with Ed Ricketts, who was quite a character, and all the challenges that they got into. This vessel was left out of Monterey, California, and went down to the Gulf of California. And of course, the HMS Beagle, the ship that the Charles Darwin took down to the Galapagos, where he wrote, ultimately collected the data to write his treaty on the origin of species. But I mention it because he also wrote a volume called The Voyage of the Beagle, which is also an interesting read, especially for those that are interested in that kind of historic perspective on research ships. I'll also say that we've seen classic research ships, we've seen some research ships in history or in literature. There's also some very unique aspects of what we'll call research ships. And I'm sure some of you, or maybe some of you in the audience may recognize this. This ship is called the Glomar Explorer. So this was built by Howard Hughes here of Hughes Aircraft, and what some folks might not know is that Howard Hughes really made most of his money perfecting a drill bit for drilling oil wells and things like that. Well, he also built this drill ship called the Glomar Explorer to look for something called manganese nodules, which are a precursor to finding oil in the ocean. At least that was the intent behind it until this was in about 1974 or so, when the Russians, at arguably one of the heights of the Cold War, lost one of their submarines off the coast, and CIA talked to Howard Hughes and says, well, can we borrow your Glomar Explorer, and you can look for what you need to, but maybe we can look for something as well. And they developed something called Project Azorian, where while they were looking for manganese nodules, they developed a crane mechanism that secretly lowered out of the bottom of the ship here to pick up the sunken K-129 Soviet submarine that was on the bottom. So a research ship with a unique purpose, I would say. There's also been some crazy designs for research ships as well, and this is probably one of the more unusual ones. This is called the RP Flip. Reversing platform, rotating platform, and you can see here the Flip is being actually towed out to sea by this tugboat here, and it's actually the bow of the platform is here, and this is all part of the ship, if you will. And this was designed at the Scripps Institute of Oceanography probably back in the 50s by some acoustics folks that were really interested in studying sound across the ocean and temperatures across the ocean. And they wanted a platform for which it wasn't rocking around a lot, and it was very, very quiet. And sure enough, they developed this thing, and this is how flip works. So you tow it out to a place, and then you start flooding the ballast, and the ship slowly starts to tip on its end, and then ultimately you can see on the right, and you probably can't see it from where you're at, but these are actually scientists that are standing right here on this ship, and everything on the boat is hinged. So every desk, every toilet, every table works in both two different directions when they flip it up. And then you can see it deployed here, so they put these gantries out the sides and they lower their instruments out to listen to sound waves. And there's almost no sound associated with this. You don't need an engine to run all the time to keep position or anything like that. So the flip would certainly categorize or be considered an unusual vessel, as I think, but one that's still in use today. If you decided you wanted to write a proposal to the Office of Naval Research or the National Science Foundation, you could charter flip if you wanted to. And I would argue that people have also come up with modifications of this and even more fanciful versions of this. You can see here, this is what they call the proposed research vessel Sea Orbiter. And they're still working on money to create this vessel, but I think it's idea that it would be somewhat autonomous and float through the oceans. And you can see here whales enjoying the Sea Orbiter here, so this seems like a magical place, but until the bill comes for building it, and the magic goes away. But nonetheless, it's certainly a proposal, and you could donate to this particular project if you so chose. But I think we could look back at a more traditional approach, bringing this back to what would be more of a traditional research vessel. I picked 4 out of here. The research vessel Sona is recently built by the Germans. It's a global class ship that goes all over the world. The Kila Moana is operated by the University of Hawaii, the Investigator by Australia, and the Point Sur here is another vessel that's an academic research vessel that all share some commonalities to each other. They have, we'll go through this later, they have an A-frame in the back for lowering and raising gear. They have cranes on board here. This crane is being deployed right here. They have satellite systems on the tops of all of them. You can see here on the Investigator. They have actually 3 different domes here, all to keep scientists engaged, keep them ability for them to do their work, regardless of where they are in the world. So this represents more of the more modern approach to research vessels, and the United States operates in what we call the academic research fleet. So this is a collection of vessels that are owned and operated either by the National Science Foundation, the Office of Naval Research, or individual universities that come together and agree on a common way of scheduling their ships. And the body that helps coordinate this is a group called UNOLS, or the University National Oceanographic Laboratory Systems, quite a mouthful. But you can see here, it's a collection of almost 18 ships from institutes all around the United States. You can see the red ships here are vessels that are part of the UNOLS fleet, and the yellow dots are institutions that operate research vessels that also benefit from the UNOLS umbrella of information exchange and lessons learned and scheduling. So you can see here the vessels here, the research vessel Sikuliak from the University of Alaska, the Thompson from the University of Washington. The Sally Ride is one of the newest vessels operated by the Scripps Institution of Oceanography. The Pelican is in the Gulf, the Walton Smith at the University of Miami, and of course the Atlantis that's operated by Woods Hole, and you can see the Alvin, the submersible submarine there also in the upper right-hand corner, all operated by Woods Hole Oceanographic and part of this UNOLS institution, which again helps to coordinate research vessels around the United States. There's another small component here that I wanted to touch on real quick, and that has to do with, in addition to the government owning some of these vessels or universities, there's also been recently quite an effort by private philanthropies to operate their own vessels. And this is an interesting component, I think, to the evolution of studying marine science and oceanography. in the world today, where folks that have accumulated quite a bit of wealth have decided to jump into the fray and build their own research vessels. And here we have examples of that. The Petrel here has done some really interesting work on locating shipwrecks around the world. This is operated by the late Paul Allen, from one of the founders of Microsoft. And there's some fascinating, their website is really interesting for, they literally have some sophisticated sonars that go around and detect historic shipwrecks all over the world. The Schmidt Ocean Institute, Eric Schmidt here, his group operates the Falcor. Eric Schmidt was one of the founders of Google. So he and his wife have developed, again, the Schmidt Ocean Institute, an interesting organization that helps to fund projects with a number of different institutes all over the world. It's one of their big focuses to engage the greater global community as well as just the United States. The Western Flyer is a catamaran vessel named after the Western Flyer that John Steinbeck and Ed Ricketts took down to the Sea of Cortez. It's operated in Monterey Bay, California through the Packard Foundation of Hewlett-Packard fame. The upper right-hand corner here, I put in quotes the Alucia 2. They're still looking for a name for this. If you all wanted to put in your oar in to name the ship, I'm sure you could log on to his website. This is a vessel that was, it was built or retrofitted by a gentleman named Ray Dalio, a very wealthy investor from the Connecticut area. And then perhaps the biggest one and most recent one is the Rev Ocean. And the picture doesn't do this justice, but this is over 600 feet long. I think it's the largest research vessel in the world. It's built by a gentleman in Norway, and I am not even going to try to pronounce his name, but he has a very interesting past where he started out as a deckhand on fishing boats in the Washington area, and ultimately worked his way up to own one of the biggest marine construction companies in the world. So this is an interesting way, evolution of how oceanographic research is conducted through research vessels that private philanthropic groups have put together. But I'd like to bring this back now to our little corner of the world, and that's the seagoing history of research vessels at VIMS. So we might not have a 600-foot vessel that's tied up in Norway, but it doesn't mean that we don't have the needs, force, capability of getting out to sea and studying these kinds of phenomena that are right in our backyard right here. So VIMS has, over the course of its time here, I put up some pictures. The Virginia Institute of Marine Science started as the Virginia Fisheries Laboratory in the 40s. You can see a very small, pretty humble little building here. It's evolved. You can see in the 50s a number of more buildings had been built, and more infrastructure, and ultimately resulting in the buildings that you see down here on the bottom here. Again, building on this incredible rich history and excellent reputation for marine science, certainly estuarine ecology and the study in Chesapeake Bay. So in order for those scientists to get to sea, we had to have some research vessels, and over the course of time, VIMS has had a number of research vessels. Make no mistake that it seems like, in my experience, and I've been at a number of different institutions, it seems like every lab director or dean wants to have their own boat. And they want it to be bigger than the guys next to them. So VIMS has, again, a very rich history of these. The Agnes Hope here, you can see towing a plankton net right here, and I found some interesting background on this, that while it wasn't being used by VIMS to conduct oceanographic and scientific research, it was also a police boat, probably to keep an eye on the oyster grounds in the area at the time. The research vessel Virginia Lee was used in the mid to late 50s, as you can see here. And one of the unique things that I see about this was that for those of folks that are used to boats, I was amazed at how small of a beam this boat has. It must be, if it's 10 feet, I would be surprised there. But yet you can see the functionality of it. These early divers here getting in to do their work. And then some folks that are really enjoying themselves. I'm not sure what kind of research they're doing, but there certainly must be something important though, right? Whoops. Look at that. Let's see if it comes back here. There we go. So the Pathfinder was also used in the mid-50s, and you can see these things, for those that can't see it, they almost look like bombs towing behind the ship. They're actually a type of dredge that you can dredge along the bottom to bring up certain samples. We can also see on the right the research vessel Langley that was also used in the 50s, which was actually an old ferry boat, as you can see here. But one of the unique aspects of a ferry boat, for all of us that have been on those, is there's one thing that they have, and that is that they're very wide and they're very stable. So from a scientist who many of the greatest oceanographers that I've ever sailed with, I hate to say it, usually get seasick. So having a vessel like this is probably very much appreciated by them. So you can see the evolution of opportunistic vessels, and we'll continue that. Here, the Pathfinder, again, a very unique design here. This was not a purpose-built research vessel, most likely was built for either fishing or buoy swapping of navigational aids. The research vessel Virginia C here in the middle has a very interesting past as well. It was a 140-foot ship that was acquired by one of the directors at VIMS, Dr. Hargis, and it was a Navy minesweeper for quite a while during the war, and then was repurposed. And as I mentioned, many different lab directors really enjoy having a larger and larger vessel. And I think, well, I didn't know Dr. Hargis personally. From what I've read, he had kept an eye on both Scripps Institution of Oceanography in San Diego and Woods Hole, and didn't want to be outdone by those two institutions with respect to vessels, so he kept wanted a bigger vessel, and it was almost his undoing, because a vessel like that does cost quite a bit of money to get and to maintain, but ultimately it was sold and eventually scrapped by the Navy. But we can see here again a continued evolution of vessels here. This is the recent vessels, I'll say, at VIMS. So these are retired, but we're getting closer to where we stand today. And you can see here the Eric Olson, the small, stout little vessel that was used for acoustics primarily. The Fishhawk was, again, you can see it towing a net there. VIMS, since probably the mid-50s, has been part of one of the most important, arguably a very important data set of juvenile fish. So tracking juvenile fish populations in the Chesapeake Bay. And when you develop a data set that long, it's so important, because it'll show you the changes, where you were and where you are now, as long as you continue to collect the samples in the same way. So a lot of these vessels that you see here were used for that. The Pelican was an interesting acquisition. You can see it's like a landing craft mentality here. It is coming into a harbor, and it's lowering its front door here in order for scientists and things to come off the front. This vessel was acquired prior to my arrival, and I'm not sure how long it actually lasted at VIMS, but it was ultimately sold, and I think people were fairly, breathed a sigh of relief when that finally left. And it leads us to our current fleet here. As we mentioned, we have over 20 small boats and a series of other larger boats. The Tidewater, again, and coming up to the largest vessel that the VIMS had for many, many years, the Bay Eagle. And the Bay Eagle was almost 40 years old. So at some point, the scientists and the director at VIMS said, we've got to figure out what we're going to do about replacing the Bay Eagle. Ships are like buildings. After a while, you have to start thinking about, I got to start thinking about replacing this vessel, and what is it going to look like? And that's what they started asking themselves. We need something more, but what's it going to be? What do we want? We don't want to end up with something that's too much or too little. And they didn't want this, unfortunately, which is probably good. So the first thing that you do on any ship build is you really have to define what it is you actually need. What do you want? So you put together, and you get a group of scientists together, and you develop something called the science mission requirements. What do you want your ship to be? And that's exactly what VIMS did. So they went ahead and defined the types of things they wanted to do. Fish trawls, coring, buoy deployments, plankton surveys, and that was what the mission was. And here's the mission requirements. These are the things that scientists really wanted to make sure, this will keep us on our toes, won't it? These are the things that scientists really wanted to, or that we felt the ship needed to have with it. It had to be stable, it had to go a certain speed, it had to have an ability to have a certain cruising range, how long it would stay out for. So once you determine what it is you want, the next thing you have to do is you have to find somebody to design it. And VIMS was very fortunate to connect with the Jamestown Marine Services Group of JMS. And they ultimately developed the drawings that you see here for the Virginia as it is today. And the drawings are detailed. This was just one of probably thousands that were created. Every aspect of the ship has a drawing associated with it that's passed off to a shipbuilder. So VIMS was, or JMS, who has a great deal of experience with research vessels all over the United States, was contracted to build this. And again, I think VIMS was very fortunate to have selected them because they came up with an excellent design. But you have to identify a shipbuilder now. So once you have the design, you have to shop it around and figure out how and who's going to build it. And this is something that's really interesting to me, and because I'm standing in front of you all, I'm going to take some license and talk a little bit about shipbuilding. I promise you very briefly, but you can see here it's evolved quite a bit from people building dugout canoes to, you can see here, Newport News Shipyard. I would be remiss if I didn't put something in here. So you can see it's a big dugout pit that you could essentially flood once your ship is built. And here we have a ship that's being built. Actually, that's the Titanic that's being built right there in Ireland. The question is how are ships really built? There's a couple of different ways you can do them. You can build them sort of as a whole, or you can build them in modules. And the modular building is more technical, but in general, I think it's used on more sophisticated builds, and that's in fact how they built the Virginia. As an example of this, so I've taken a much larger ship to give you a very brief background on how this is done, and it's pretty amazing, at least I find it amazing. You can see here, a giant cruise ship like this is all built in small little chunks. Starts out as a flat panel here, you add more structure to it, like building a house of cards almost. You build more, you can take these modules and incorporate it into these, and they weld all together. Again, you can see the layout of each one of these. So somebody can be building this R1 module, they don't know where it fits into things, but they know exactly what needs to be in this module. And then that's brought together, and they simply weld them in place, weld them two of the modules together. And what's amazing, you can see on a 900-foot cruise ship, it's built the same way. And it has to match up, you can imagine, within less than a half an inch. So you could have a module that's as big as this entire building come together, and it's got a weld and made up with another one that's identical to it. And if it's off more than about an inch, it won't work. So I thought I would show you just briefly, in some of my travels, I've had an opportunity to visit a couple of different shipyards, and what I found amazing was that all the cruise ships that you travel on today of any size, for the most part, are built in one place. And that's in a small shipyard in Germany. Or not a small shipyard, it's a very large shipyard, as you can see here. And they're all built in the same sort of modular way that I just described. The shipyard is in a place called Papenburg, Germany. And you can see here, here's one of the first bottom modules of a cruise ship. These are all little people standing here. There's always some glory shots that usually administrator, you can bet that, all the people that are standing in front of that ship right here, this right here, not one of those guys has ever been holding a screwdriver, a hammer, a welder, but they're getting a great shot. But you can see here, as I'm going to try not to trip over my cord, here's a little bit more of the building of that particular module. You can see them coming together. And what's amazing, you can see here, these are all built in these big, giant warehouses, biggest things you've ever seen. And here's a cruise ship that's literally coming out of it to make room for these things, which are actually the modules that they've floated and which will ultimately have to come together. And then the workers will come by and weld every single aspect of these modules to create the big, giant cruise ships that you see today. My thing keeps wiggling out here, and then the next phase, of course, is the outfitting. So once these giant behemoths come out, you can see the size of these ships is truly amazing. The image on the bottom here shows you the kind of outfitting that would go into almost a 900-foot cruise ship. Pretty amazing, and all done. And again, I can mention that the town of Papenburg is incredibly small. And what's interesting is that these cruise ships are not, you'd think that they would just keep building them bigger and bigger and bigger. The problem that they have is in the delivery of the ship. the last part of that, because Papenburg is on a relatively small river. So you can imagine if you're standing in a field like this gentleman here on the left and seeing that go by, they're literally limited on the size they can build these ships by how big they can get down the Ems River. So you can see there in the bottom right, I don't want to go over there, my computer will shut down. They're literally squeaking these cruise ships out of these. Yes, exactly. And I think on either side of those two are a bunch of insurance brokers going, oh, please don't hit me, please don't hit me. No, it's fine, it'll work. But nonetheless, the build of the Virginia didn't make it all the way to Germany. We selected a shipbuilder in Quebec, actually, in Matane, Quebec. And this was done through a competitive process. And most of the yards, certainly in Virginia or locally, were more interested in much larger builds than the research vessel Virginia, so that we had less interest in those. We were fortunate to find a builder in Quebec at the time who had a lot of expertise and built ships in that same modular fashion that I just mentioned, that the giant cruise ships are built in. So we ultimately, Lamerdin Maritime was selected, and off we went. And I'm going to show you a couple slides of the actual building of the Virginia. And in keeping in mind, I put the slide in the upper right-hand side there that reminds you, again, just you don't have to pay attention to the details of it. But remember, things start out as a flat plate, just like this, when you're building a giant cruise ship or a 93-foot research vessel like the Virginia. So this is, in fact, the aft deck of the Virginia, just starting out. And they build more onto it. So again, it's being built sort of upside down, if you will. And you can't, in the case of Lamerdin, and as well in those giant cruise ships, they can build these modules in different places and bring them together as they need to. And in Lamerdin Maritime was no exception. So they built the bow section in a different place. And you can see it coming together here, again, upside down. And we build a little bit more on the top of it. And here's more of that. So we've got half the ship here upside down in a different building. So, which just seems kind of crazy. You can see here that big hole on the top we'll get to later is where the bow thruster on the vessel is placed. So you have to take them outside and you have to flip it over. And that's exactly what they do. It's amazing in Papenburg to see these done with probably a 400-foot module being flipped upside down, which they have giant cranes for. But it's the exact same technique that Lamerdin used here, where they take it outside and they flip it over and put it back together, put it back up right side to finish their outfitting of the vessel itself there. So what's also interesting about building in modules is that you can, I don't want to walk over there on my computer. You outfit the entire inside of that particular module. So you can see the insulation going up. They'll put in various different walls, electronics, piping, everything. So when those things, again, come together, they all are welded together. So that's what you're seeing here. And then again, ultimately results in what you see here, the research vessel Virginia. So the Virginia itself was, as you see here, 93 feet long, a 28-foot beam. So it's in the interest of ships, that's a very beamy vessel. So, and we'll get to that in just a second. It draws 9.5 feet. We can put 20 tons of science gear on the back deck of the vessel and still operate safely within what we'll call the stability of the vessel. We don't want to put too much weight on it so that if it starts tipping one way or the other, it'll tip over. The Naval Arcs calculated that we have a 20-ton limit, and it can accommodate 13 people. That's scientists and crew, which is an amazing compliment on a vessel that's only 90 feet long. So what I wanted to do was continue down this line and go through a couple of the more unique aspects of the Virginia here. And one of the things that most people come and mention to me is, what's the deal with the bow of that thing? What is going on there? And it is a very unique bow. The Naval Arcs call this a plumb stem bow. And it has a couple of different unique aspects of it. Probably one of the more important parts of it is that it actually extends the waterline length of the vessel. So what does that mean? Ultimately, that translates into something called the hull speed of a vessel. So every vessel has a certain amount of speed is how fast it can go. And even if you put bigger and bigger and more engines on it, the vessel really can't go any faster because it's not long enough, if you will. It needs length in order to gain more speed. Otherwise, you're just cramming something through the water. The plumb bow like this adds to that waterline length. A lot of ships are tipped like this, so the bow is much further, it's over the top of the water. And where the water actually hits the hull of the ship is smaller than where the actual bow is out the front. This allows longer length at the waterline and allows us to have a little bit more increased speed. So it's a little bit more efficient in that respect. It also allows us to sink that bow thruster deeper in the water. The bow thruster helps maneuver the ship around. And it also helps to do something that we call reducing bubble sweep down, and we'll talk about that in a little bit. But when the boat goes through the water, bubbles are formed, you know, just like the bow wake of a ship you guys have seen. Well, that's really cool when you see it, but if you're a scientist and you put some instruments under your boat, bubbles really create all kinds of bad things for you. So this bow design helps to reduce that a little bit. So that's one of the more unique aspects of the Virginia, as everyone sees. We have a main engine and reduction gear that's kind of interesting. So the vessel only has one propeller, but it has two engines associated with it. And we can run one engine or two engines in this vessel, so that's where our redundancy comes into play. Most of the times when you guys go out to sea, if you have your own personal boats, a lot of times you have a main engine and sometimes you have a kicker on the side, so that if the main engine breaks, you always have some way to get back home. Well, the scientists feel the same way about getting back home to their labs and things like that. So the redundancy here comes into play of having two engines that fall into a common marine gear that you see off to the right here. It's a big giant disc, if you will, and the two engines go into that. And it, in turn, turns one single propeller that will turn the propeller that you see there that's connected to something that we call a controllable pitch propeller. So there's no transmission on the ship. We don't have a forward and reverse gear. What we do is we have the pitch of the propeller blades change, and that's what makes the ship go forward or backwards. So imagine if you were standing in front of a fan, if the blades on your fan were perfectly flat, no air would come at you. But if you pitched your blades and turned them, that's when you get wind coming at you. It's the same principle here. So we can adjust the pitch of the prop blades to allow the ship to go forward or to go backwards without having to shift a gear. So it's kind of an interesting aspect of the ship. And we also, off that main engine gear, for those that are interested in more of the engineering aspects of it, we control and have a whole separate set of hydraulic pumps that are associated with that and motors that allow us to power some of the hydraulics on the vessel off of that marine gear as well. One of the things that I mentioned about was the maneuverability of the vessel. So outside the back of the propeller, we have a triple rudder here. So the rudder is actually what will steer the boat. We have three of them positioned right behind the thrust of the propeller. So this allows the captain a great deal of maneuverability of the ship, which is really key on a research vessel because they always want to get places and make tight turns and go wherever they want to go. So this allows the captain quite a bit of flexibility on operating the ship. We have a bow thruster. So a bow thruster is, and this is a 250-foot, it's a flush-mounted bow thruster, and they call it, it's a pump thruster, if you will, where water is sucked up into this grate and then it's shot out of this grate. And the way that the bow thruster works is this grate that has a bunch of louvers actually rotates 360 degrees. So wherever the water is rushing out of, the ship gets pushed in the other direction. So the unique aspect of this is it's flush to the boat like that, and it gives a lot of control over, again, how the ship can maneuver. And it also is our backup to the main engine. If the main engine, for whatever reasons, broke, we could actually run this bow thruster and get the ship home, albeit very slow, but at least it's a backup. So, and I drew an arrow to show you roughly where the bow thruster is, right on the bow of the ship. We talked a little bit about stability on the vessel. Remember I mentioned how beamy the boat was, how wide it is. And that's an important capability. Remember our talk about the Langley was an old ferry boat that was really wide. Well, you can see here, there's almost a little bit of similarities you see on the stern of the Virginia being very wide. It also has a series of two, what we call skegs, and these are large, almost keels that come down on either side. There's one on either side of the propeller that actually help to provide a great deal of stability in the boat, also gives the captain a more effective way of running the ship at slower speeds. So that helps to make the boat more maneuverable and more stable. It has some very unique cooling aspects of the boat. You can see here in the upper right, we call these things tube nests. And one of the important things about operating a vessel this small is it can get in shallower places. And when you have shallower places, there's times where you can get very close to the bottom. And we don't want to have anything external to the hull of the ship, or it could break off or damage. So we put the cooling mechanisms up in these little compartments that you see here. So you can just barely see, I know people in the back can't see this, but these tube nests that you see there are inside these grates. Water comes in there, and the hot water is circulated in those tubes, and the ambient water in the ocean is what cools them. So it's kind of a unique aspect to the boat in that they're protected up into the ship. But one of the problems with that is now you've got a whole big cavity in the side of the ship. How are you going to keep barnacles and marine growth from growing in there? Well, that's where you have an active anti-fouling system. So in these things, you'll notice that they're pretty pristine inside of them. And that's because we actually have an electric system, if you will, of these giant copper rods that are in each one of those individual compartments. And you can see from this side here, this is a big giant chunk of copper. And what we're doing is putting a small, subtle electric charge inside this compartment. And the charge itself is enough to dissuade barnacles and oysters and mussels and everything like that from growing within these areas. Because it'd be very difficult for us to get in there. And if you see on these tubes, boy, getting in and out of these little crevices and cracks, we'd have every single barnacle and their brother up in there. So these systems right here allow us to not have to get in there and paint all the time and chip out barnacles. But we actually had a problem with one of them. You can see the way they're supposed to look in the upper right-hand corner. We had one that went bad. So the copper itself ate away very, very quickly because it wasn't bonded correctly. The system wasn't functioning correctly and bonded to the hull of the ship where it needed to be. So it was just eating the copper away way prematurely. So we had to replace that in the last shipyard period that we had. And ultimately, although I'm not sure if the folks in the back can see it, but we had a brand new large spindle of copper in there to keep us going. So these should last at least 2 years. We also have some interesting covers on the back of the ship and on the side. Not sure if you can see it, but these are actual pieces of plastic, UHMW, ultra high molecular weight plastic that's formed and bent around the back of the ship. And we do a lot of trawling on this ship. And for those that are know fish trawling, there's doors that are associated with it. They're big metal doors, and we bring them up tight against the stern of the ship. Well, each time you do that, we would be chipping off paint and denting the ship and everything like that every time we did it. So the folks that were designing the ship decided to add these plastic coatings on the back and on the side here in order to help protect the ship a little bit more. Every research ship has winches and wires. As we mentioned, remember the Challenger had 181 miles of rope to go down and make soundings. They run all those off winches. We have those winches as well. And what you see circled here, we have dedicated winches for pulling trawl doors in and out. We also have a hydrographic winch for lowering instrumentation that has a conducting cable inside of it, like a long extension cord, so that we can power instruments 2,000 meters below the surface of the water. And we can also have user-supplied gear like the net reel that you see in the very back of that. So scientists can bring their own gear and we can plumb them into our hydraulic systems. Of course, ways of handling heavy loads. We have an articulating crane right in the middle there, and you see in the upper right-hand corner. And this crane right here is actually, they call it an articulating crane because it's kind of all bent over. But when it opens itself up and telescopes out, it has a 30-foot range. And at that length, we can still pick up 2,600 pounds. When it's close in, we can lift over 11,000 pounds with this small little crane that's mounted. And the important thing about that is it can reach all over the whole back deck. The side J frame is used to deploy gear right off the side here, off the starboard side. And of course the A frame, which is what we had mentioned earlier, is ubiquitous on practically any research vessel, really needs to have an A frame for deploying and recovering gear. The other interesting aspect of our build here is that we've got these instrumentation or acoustic instrumentation mounting pods. So these are two special areas under the ship that we can mount oceanographic sensors in them. There's one on either side. I've pointed it out here. They're located right in the bow of the ship. And you might say, well, why would you need something like that? Why don't you just mount it into the hull, like everybody else puts an echo sounder or a fish finder in the hull of their boat? Well, I mentioned about bubble sweep down, and this is where we can get the sensors mounted into these systems, into these pods, and the faces of them are out here. Bubbles tend to follow right along the hull of the ship. So by mounting these down lower, they're outside of where all the bubbles that come down from the bow of the ship. So it gives the scientists a cleaner way of collecting their data. Bubbles wreak havoc on acoustic measurements because it's hard for acoustic noise to go through air, which is what a bubble is. Completely messes up the signals. So there's two of these pods, and it allows us to mount scientific instrumentation on them and provide scientists with some of the best data that they could possibly have from acoustic sensors. So again, a pretty unique aspect of a research vessel as I see it. And of course, we have the usual stuff that you have in a vessel. We have an autopilot, electronic charting, closed circuit TVs around the ship. But one of the more unique aspects of the Virginia, and something that's found almost exclusively on much larger research vessels, is something called the dynamic positioning system, or DP. So DP, or dynamic positioning, allows the captain a great deal of control over the boat. It allows you basically, it incorporates both the thruster, the propeller, and the bow thruster to work simultaneously, where the captain can basically push a button at a particular site, and the ship will control and keep on that station no matter what the ambient conditions are. So if it's blowing like crazy, he can push this button, and the main engine and the bow thruster will work together to keep the vessel within 1 meter of a particular site. And this also comes into play when you're actually doing a survey. If you want to stay on a straight line, the dynamic positioning system will keep you on that line. Now, it's different than an autopilot, because an autopilot will go to a particular point. So you could be going off course, and the bow can still be pointing at your site on your autopilot, but you'd be way off course, even though the bow is still trying to get to where it needs to be. Dynamic positioning will keep you dead on a particular track. And again, this is a ship. The dynamic positioning is something that's almost exclusively found on much larger vessels. So the Virginia, being a smaller vessel, makes it very appealing to scientists and other people who are interested in the vessel, because they can basically utilize a small vessel like this and not have to pay a big 300-foot vessel price, if you will. So habitability, of course, is key on a ship like this. 93 feet. The folks get a little bit cozy on a ship like that if you're out for 20 or 30 days, if that's what we do, not in one trip. So you can see here we have a full galley, the kitchen here, accommodations, the head and shower, the bathrooms and things like that. Meridian Maritime did an excellent job with the build of the vessel, and you could tell that in the bunks, in the woodworking and things like that that's found throughout the vessel. And of course, every research vessel needs a laboratory space, and we are no exception. We have both a wet lab and a dry lab space, so scientists can use their computers, write out their data, work on mapping computers and things like that in one part, and then they can have this that I'm showing here, the wet lab, where they can bring in fish or sediment cores or plankton and do their manipulations there. We also, throughout the vessel, we have these, for those that can't see them, there's little dots here. These are actually sockets in the floor. They're actually throughout the laboratory, and they're throughout the entire back deck of the vessel. And they're measured very specifically 24 inches on the center of each of the bolts. And that's so a scientist anywhere in the world who's interested in using the Virginia will know that if they want to mount a winch or a piece of equipment, they can develop a plate, and they know exactly that they can make this plate 24 inches on center, and that it'll be able to fit anywhere on the ship that they need to mount it. So it provides a very unique way of dealing with that. So why did we need this vessel? And this is why. So here's some of the science that's been done on the ship to date. And again, this just came to VIMS last year, so it's fairly new to us. but you can see here, these are big trawls that they're doing for some of the fish trawls that VIMS has been a part of for over 50 years. You can see some of the larger organisms that have sampled. Here's a hammerhead shark. All of the sorting tables that we're able to bring out. And again, a research vessel like the Virginia is kind of like a pickup truck. It has to do a little bit of everything. So you have to be ready to do fish trawls, as well as plankton tows that you see here. You take advantage of an A-frame here to deploy and recover sophisticated sonars. And this is a really interesting, the A-frame being so tall on the Virginia, these folks here are doing a coring evolution. So they're going down and coring the bottom using something called the vibracore. So you lower this thing down to the seafloor, and the top head vibrates to the point where you can get into very sandy, hard-packed sediments, and then pull them out, and then the scientists can study each individual layer to see how sediments and things have moved around. So the Virginia can do all of those things. The one thing that we didn't get a chance to do, and in any ship build, it's probably like building a house. You have this great idea when you build your house, and then when you get about 3/4 of the way through it, you go, geez, kind of running out of cash. What am I going to chop off in order to finish this project? Well, building of this ship was no exception. There were a couple of things that had to be de-scoped, we call it, until later, and one of those was some pieces of scientific equipment that we're very close to actually acquiring soon. And there are two pieces. One of them is called a multi-beam sonar, and it generates things like this. And the other is what's called an EK80, which is a really fancy fish finder. Both of these are sonar suites. So a sonar, the multi-beam focuses on the bottom, generating bottom maps. And the EK80 is actually, like I said, a fancy fish finder, but it's fancy enough that scientists can use that data of the results coming back from this to actually define what type of fish are actually under the boat. So they not only can tell presence, they can tell groups of fish, if they are sharks or rockfish or something like that, and they can tell that through sonars. It's pretty impressive. And of course, this equipment is very expensive, but it's key. Again, usually found on much, much larger vessels. And I thought I would just show you briefly, one of the things about larger vessels is you can put stuff anywhere. Well, in the Virginia, we've got to be real careful about where we put stuff because we don't have a lot of space to put things. I've shown you here roughly the way a multi-beam works, which is what multi-beam sonar is. It emits sound down, you can see here, if you will, these inner rings, and looks for the reflected signal back. And from that, it generates a very detailed map of the seafloor or anything that's under the water. Bigger ships, like I said, the German vessel Sona has something called the gondola system, and the whole bottom of this is part of their sonar system. Remember, that was about a 400 or 500 foot ship. This is, so this gondola, again, is below the profile of the ship, so those bubbles don't get to it. The sensors on this are probably upwards of $5 to $6 million worth of sonars. So they want to make sure they actually work. We didn't have the space on the ship to put a gondola system. Plus, we didn't want to accidentally stick it in the mud either and wipe off our sonars. That would be about $1 million worth of sonars. So another alternative may be a drop keel. You can see here, on some ships, they've opted for this little keel that can retract, goes up and down in the ship, and you mount all your sonars in there. Again, the idea being is you get it out from below the hull of the ship to keep it from getting hit with the bubble sweep down aspects of a vessel. You can see here, this was on a Norwegian research vessel that was recently built. Looking at the bottom of it, you can see roughly this is where that drop keel is located. Very far away from where the propellers are, which is really important because the propellers make a ton of noise. So you want to keep that away from where your sonars are. But again, because we didn't have the flexibility to have a drop keel, and we didn't have the space for a gondola system, we opted for what you see on the right, which is a pole-mounted system. And this is a system that has been used in many different applications. You can see here on a very large ship, the pole sits here, and when it's deployed, it flops down like this, and we can go ahead and do our profiling and our sonar work. You can see it on smaller vessels here. Some people mount them on the bow, but you can see here, this is more likely what the kind of style that we're going to have as we develop our system for the Virginia. And the importance or the uniqueness of a pole-mounted system is that if for some reason the sonar isn't working right, we can just pull it up and fix it. Whereas if it's mounted permanently on the hull of your ship, you're gonna have a problem when you have to do some maintenance on it, potentially have to pull the entire ship out of the water. And so I alluded to it, but what can these things do? The maps that you see here are some interesting aspects of what a sonar can do, similar to what we're going hopefully to install on the Virginia. And you can see here, this is a measurement of a subsurface volcano. So the multi-beam map will map every little detail, things that are less than a half a meter high, actually less than that, probably a quarter of a meter, will be seen from this. The sonar that we're gonna get on the Virginia will measure down to over 600 meters. And we wanted something that gives us high resolution in shallower waters because that's where the Chesapeake Bay is, and that's where most of the places where the Virginia is gonna be operating. You can see again here another map of a continental shelf, if you will. And just as important is we can also use these multi-beam sonars for detecting old shipwrecks as well. I mentioned the research vessel Petrel that Paul Allen had. Uses the exact same type of system, same theory as what we're proposing on the Virginia. Locating shipwrecks is kind of an interesting aspect, as I'm coming to know in this area, because there's lots of them. The state just recently, I think, re-implemented a marine archaeology position, and we hope to be able to start working with them a little bit as we get our system online and to identify any areas of potential and actual shipwrecks. The researchers at VIMS are also very interested in this capability because you can actually see sand ripples on the bottom. It's so sensitive. So you can get an idea of where the sediments are moving under the water. Are they building up in places? Are they actively moving, and those kinds of things. So with that, I will ask you if you have any questions. Please.
Any fouling?
Yeah.
What type of paint do you use, and do you paint every year or every other year? What on the bottom for any fouling?
No, it's a great question. As a best marine practice, what we tend to follow in on the Virginia is we haul the vessel out at a minimum twice in 5 years. So every 2.5 years, the vessel comes out of the water. We pressure wash it and we apply paint to it. So
What paint do you, what kind do you use? Many types of any fouling.
we use an ablative anti-fouling, which is a type of paint that is designed to slough off over time.
That's what I use in mine.
Yeah. So, in the back.
You mentioned the dynamic positioning. I was wondering how that works, because do you have something on the bottom and you use sonar or radar, or are you using GPS or a combination of all sorts of things?
Yeah. No, another great question. So the dynamic positioning system on the boat, which again helps to steer it or keep it on its location, is integrated into the global positioning system, the GPS we have on board. So it's really a computer on the bridge that has a position from satellite that tells it where it needs to go. And the dynamic positioning equipment controls the engines and keeps it online. So it uses satellites, not necessarily sonar, to keep on track on these kinds of things. So, yeah.
Who make up the scientists on the cruises?
So the research vessel Virginia is essentially available to support any kind of research, oceanographic research. So the scientists themselves will come either from VIMS, or there'll be scientists that have written proposals to federal or state agencies to use the vessel. Or they could be from outside charters, so marine geotechnical groups that have a research focus on what it is they're doing. So it's a real breadth. Scientists at VIMS and classes can also use the vessel as well. So they could bring out, let's say, an introductory class in oceanography, would come out for the day. But in general, we found that most of these are funded by the National Science Foundation or state funded through projects that are mandated by the state that we continue to do. So, yeah.
Long-term goal is to keep the vessel home berth on Carter Creek?
Again, another great question. I would like to see, and I think, I was just chatting with the director of VIMS, Dr. Wells, about this. I think everybody would love to see the vessel in Gloucester Point. But right now, our facility in Gloucester Point, where VIMS is located, doesn't have the water depth to safely bring the vessel in. So collectively, I think on the long-term capital improvement plan is to redesign our boat basin to facilitate that. It's a couple years out, but it's something that is definitely on the horizon. I think everybody would like to see. If not that there's anything wrong where it is, and as a matter of fact, there's a lot of benefits to being up on Carter Creek, primarily because when hurricanes come through or anything like that, it's a very protected area. But I think from the interests of providing that identity and having that really part of the VIMS fleet and taking advantage of our infrastructure and research or resources right there in Gloucester Point, we'd like to see it come back to VIMS eventually.
And follow up, do you have any plans for public tours of the vessel?
We, because of our schedule, it gets a little touchy on when we can schedule some of those, since the boat is actively, we're going and coming from a lot of different research ships or cruises. We have, right now, if things go according to plan, we have almost 150 days at sea scheduled throughout the year. Not one trip, but a whole bunch of little ones. So it's kind of difficult. So we schedule those where we can, but we don't have anything formally scheduled yet. It's something that you could reach out to our media relations person at VIMS and work with them, and we can see if we can get people out to the boat, because it's something that the crew's very proud of. Yeah, in the back.
Non-technical question. You said this boat that was named the Albatross. Now, my connection with the Albatross was a poem, and Albatross is not a good thing. And why is that the name of the boat? The other thing is, I know there's a place, I think, near Belize, that's a very deep hole, and they went down to the bottom and they found gobs of plastic and crap.
Mm-hmm.
So, are you all doing anything about that kind of thing?
Yeah, great questions. Yeah, and albatross clearly has a negative connotation. An albatross around your neck. Literally, I think that's what happened. But I think the names of the ship were predominantly based on an albatross at sea, which has an incredible wingspan, and they glide sort of effortlessly in the open ocean. And for those that have been fortunate enough to see these, they're incredible birds. They have such big wingspan that it's funny, when they land, if there's not enough wind for them to take off again, they're just stuck. They can't leave, they're so big. So they spend most of their time in their lives flying around. So I'm guessing that that's where where a lot of that happens. So, Ernie, do we have a couple more maybe? Or
Maybe one more?
sure, and I'll be happy to stick around. You can come chat with me. I think this gentleman had his hand up.
I have been past your vessel so many times, and I just want to say that the biggest surprise that I have for being here today, I thought the thing for sure was built by leftover parts by Caterpillar tractors. And the fact that it's, been designed and built by marine builders is a real eye-opener. So thank you for doing that.
Thank you. Thank you, guys. And thank you all for allowing me to come chat a little bit about the history of research vessels and the research vessel heritage.